Hi, we are ME56 and our project is Cloudbot's Autonomous Atmospheric Explorers. I'm Ava and my teammates are Chris and Akash, and our faculty sponsor is Dr. George Matthew. A little bit of overview of our sponsor, Dr. Matthew. He got his PhD from the California Institute of Technology and is currently in the UConn's Mechanical Engineering Department as a fluid dynamics professor. In the US, tornado warnings are a mere 13 minutes on average, which is very little time to safely get everyone evacuated. We want to help alleviate this by building a device to collect live storm data so that we can buy people more time to find safety in weather disasters. So, the purpose of this project is to investigate, design, build, and test a Cloudbot weather balloon to quickly communicate live atmospheric measurements. We built our Cloudbot with a rugged design so that it can accomplish this task at relatively low cost and, at the same time, adhere to the Federal Aviation Administration regulations. The main operating principle of the Cloudbot is variable buoyancy. So as you can see from the GIF, the helium balloon at the top has a fixed amount of helium and provides us with an upwards force. The Cloudbot will go up when the air cell at the bottom is not pressurized. If we want the Cloudbot to come back down, we pump in air from the atmosphere into the air cell, and this compression causes an increase in pressure and therefore an increase in density as well. By making the overall Cloudbot more dense, it becomes heavier, bringing it back down. The software that we use in the Cloudbot is Arduino with Python, and we also use SolidWorks to do some CAD modeling. For recording data, we have altitude, pressure, and temperature sensors, and collect live data and have mid-flight data transmission.
This preliminary top-level model of our Cloudbot gives a good idea of the main components and the overall dimensions of the Cloudbot. When fully inflated, it's going to be roughly 11 feet tall. The main components of our Cloudbot are the helium-filled balloon, which provides the buoyancy force, the payload, which houses all of the electronics and sensors, and the pressurized air cell, which allows us to achieve variable buoyancy. Here's a closer look inside of the payload section of the Cloudbot. The tan bed shown here was 3D printed to neatly house all of the components in a compact package. A foam damper was used to help dampen the vibrations produced from the pump and to prevent it from damaging the rest of the payload. A sensor container with a repeating hole pattern allows us to easily mount sensors and route wires to the rest of the payload. We designed our Cloudbot around these critical design parameters, and then calculated the theoretical performance of our design using fluid dynamics and force balances. From our calculations, with a required helium volume of 1.9 cubic meters, we'll be able to achieve roughly 0.4 newtons of force in either the upward or downward direction. This correlates to a 1.6 meters per second terminal velocity in either direction. From testing, we found that the total pressurization time from 0 to 3 psi, or vice versa to depressurize, was around 3 minutes. This is the air system that we developed for the Cloudbot, which directs airflow to and from the air cell. When the compressor pump is running, we can open solenoid valve 1 and close valve 2 to allow air to flow directly into the air cell. When we turn off the pump and close valve 1, we can open valve 2 and allow air to escape to the atmosphere. In either configuration, we'll be able to monitor the pressure inside of the air cell with the inline pressure sensor to ensure that we don't exceed the maximum allowable pressure. One of the biggest challenges that we faced when approaching this design was creating a reliable air cell that had a high volume, a low weight, and a high tensile strength when under pressure. The first iteration that we tried was a template similar to a beach ball where 6 panels all intersected at the top and the bottom. With this method, we were able to achieve roughly 1.92 psi before failure. For our second iteration, we used a new template which only required 4 panels and had a maximum of 4 intersecting panels at one point. With this approach, we were able to use a double welt seam, and we were able to achieve 3.375 psi before failure. For our final air cell iteration, we used a similar design as iteration 2, except this time we incorporated a second layer. The outer layer was the same, which was a 40D ripstop nylon layer, except we included a 70D ripstop nylon inner layer, which provided a little more strength to our design. With this iteration, we were able to successfully pressurize the air cell to 3 psi 3 times without failure, and it's the one that we will use in our final design.
The 2 Arduinos we use run all the Cloudbot software. The onboard Arduino is able to collect all our measurement variables, including internal temp, external temp, pressure, humidity, altitude, longitude and latitude, LiPo battery, and 9-volt battery voltages, and then finally the air cell pressure. It's also able to switch our air cell into 3 different states, which are maintaining pressure, releasing pressure, and pressurizing by activating the necessary relays to control solenoids and pumps. Finally, it's able to receive instructions for either altitude targets or pressure targets and switch into the right pressure states to complete them. The ground Arduino acts as our controller and is able to receive all the information being sent from the Cloudbot, plotting and printing them, as well as sending commands to the balloon via either laptop input or the buttons installed on the controller itself. Here we can see the full electronics layout for our system. On the left are the onboard CloudBot components. In the middle, you can see the Arduino Uno in red, with all its sensor inputs on the left side and outputs on the right, showing how the relays control the solenoids and the ESC controls the compressor. On the very right side are the components for the ground control system. The ground control system is made up of an Arduino Nano with 3 buttons as an input and a transceiver hooked up to it. On the right, you can actually see our final build with everything wired together, and on the bottom center is the 3D printed enclosure we're planning on building for the actual controller itself. Next, we can see all the electronics for our air system build. For simplicity of testing, we've replaced one of the ESCs for the compressor with a relay. The 3 relays are shown on the bottom right in blue, and you can see the top right where all the solenoids and pumps are hooked together to form our full system. The top 2 images here show the sensor wiring on the left and how we wire up the transceivers on the right side. The bottom shows some of our testing from different sensors, including our atmospheric breakout, as well as getting longitude and latitude values from our GPS.
Here we have an animation of the payload assembly showing how it houses all of our electronics and pump. This is our helium connection, which will attach to the bottom of our helium balloon and allow us to pump helium into it. It is a simple assembly consisting of some PVC and a valve that we can open and close, allowing us to reuse this balloon for multiple tests as opposed to having to tie off the balloon, pop it, and get a new one every time. Though not included in this video, we will have full rig testing complete by demo day, which includes the full assembly of the helium balloon and the payload shell, in addition to the air and electronic systems we talked about in this video. Thank you.